All right, guys, so let's keep going from where we left off before, because last time we talked about atomic radius, right? And we talked about the like what affects atomic radius, and we talked about the trends of atomic radius in both a group and a period, right? So in a group, family, or column, remember it makes the chemistry, right? A chemistry, right? Small at the top, and every time you take a step down, you're adding a layer, so it gets bigger. You add a layer, it gets bigger. You add a layer, it gets bigger, so on and so on and so forth, right? So smaller radius at the top, much bigger radius down at the bottom. That's the trend in the group, or the column, or the family, or whichever you want to say it. Now in a period, as you go from left to right, right? As you go from left to right, it's going to get smaller and smaller and smaller. And the reason being is that in the same period, you have the same number of energy levels and therefore the same amount of shielding. And so every time you add one more proton, you're adding just a little bit more proton pull, right? And so with the same amount of shielding, but more proton pull, those protons are able to squeeze those electrons in just a little bit more. So every time you take a step to... Did I say left? I'm a knucklehead. It's every time you take a step to the right, silly pants. I'm looking at the camera and I'm going like this. I'll get better in a minute. Better. Okay. Yes, it's definitely every time you take a step to the right, you add one more proton and it gets a little bit smaller. Maybe I should finish my coffee before I do this. Nah, it's not going to happen. Anyway, factors that affect atomic radius, definitely number of energy levels, because those are like shells, right? So the more energy levels you have, the more shells you have. What else was there? Oh, shielding, right. So the more layers you have, right? It's like the inner layers block the outer layers. And the analogy I used was like that makes sense to me anyway, is like when you sit in an audience, or like if you're watching a football game or something like that and you're way back, it's like you almost have to look through lots of people to be able to see what's going on. And it's kind of the same thing for those outer electrons. You have to see through the inner layers before they can sort of like see the proton, for that proton pull to like hit it and like make it stick. You guys get what I'm saying? I'm sure you're picking up what I'm putting down. All right. So today we're gonna move onward and upward. And so that was atomic radius and the trends of the atomic radius in the periodic table, columns, periods, and now we're going to look at some of the other properties that of the elements inside the periodic table. And the first one we're going to look at is electronegativity. So I don't know if you remember what electronegativity is, but I'm going to need you to. So if you don't, you best. Hold on, technicals. Difficult. Okay, there you go. Electronegativity. This is the now this has to be memorized. See, now it's an underlined word. It's like all that thing. So we really got to dial this in. Electronegativity is the strength by which an atom attracts electrons to itself when it is bonded to a different element. This is... Pause. Okay, we're back. Sorry. Technical glitches again. Okay, so electronegativity. What was I saying? Yes, electronegativity is the strength that an atom pulls on electrons when it is bonded to a different atom. And this is actually really important, this different part. Because two atoms, if they're the same element, right, they're pulling on electrons exactly equal, because two atoms of the same element are indistinguishable from one another. So this electronegativity is like a relative strength of how strong these atoms are pulling on electrons as compared to other elements. And this is just about it right there. You know what I'm saying? Atoms' tendency to attract. She's falling for him. Get it? Because he's so strong. You got to take what you can get in chemistry. All right, so listen. This difference in electronegativity, it's going to tell us how equally or how not equally, to be honest, elements share electrons when they bond. So if you think about it, when two atoms come together and like a chemical reaction happens, it's almost always because electrons are being shuffled around, right? Well, how do we know who's going to take electrons? How do we know who's going to lose electrons? Will it even happen? Because it doesn't happen every single time. Because look, watch, I'm going to take two atoms and make them come really close to each other. Nothing happens. Why? And then why is it sometimes when other atoms come into contact, there's like why? What's up? Why? Well, electronegativity is why. It helps us understand who's going to take electrons, who's going to lose electrons, and even if it's going to even happen, right? So a big electronegativity means that it pulls on electrons towards itself strongly, all right? Oh, also, not for nothing, I don't know if you've noticed, but on the back of your reference table, behind the periodic table, like on the next page, there's like a whole, it's called Table S. There's a whole list of chemical and physical properties, including atomic radius. You can just look it right up, and electronegativity. Table S, right? You can look up electronegativity. It's like right there. So you don't have to memorize it. You just kind of have to look it up. So yeah, larger electronegativity means a stronger pull on those electrons when it's in a chemical bond. The lower the electronegativity means like the weaker, which is why when we talked about earlier about the metals, they have a very low electronegativity because they don't pull on electrons like at all. They have almost no ionization energy. So metals lose electrons. Nonmetals have a very, very high electronegativity. Right, so they are pulling on electrons like crazy. So you get a nonmetal near a metal, those nonmetals are going to rip those electrons like right off. And that's what happens. So of course, we need to look at a trend in the periodic table in the family, right? So the electronegativity decreases down the family, and here's why. It's because of the old chemistry thing, right? So remember how I told you almost everything's going to come back to radius? So as you take a step down in the group or the family, or as your atomic number increases in a family, the radius gets bigger, right? So these electrons are much further away from the protons the further down. I mean, look how close that is. The further down you go, the further away those electrons are. And if the electrons are far away, they can't be pulled. There can't be a strong pull, because remember, these things work very similar to magnets. It is not the magnetic force, but all forces in nature work pretty similar. So if electrons are close to protons, there's a strong attractive force. That's like this guy right up here. But if electrons are far away from the protons, that's like a very weak attraction, and that's more like this situation down there. You dig what I'm saying? So it's like distance away from the protons. Also, there's more shielding. So the lower you go, I didn't draw them the first time. So the lower you go, the more layers there are. So these protons have to work really hard to try to get to those electrons, and like vice versa, because there's like not just this one electron out here, there's this whole cloud of electrons and this whole cloud. The whole shielding effect. Is that, you guys get what I'm saying? So as you go down the family, right, as you take a step down, it gets bigger, and therefore the electronegativity, the radius gets bigger, and therefore the electronegativity gets weaker or smaller. It's like inverse. Radius goes up, electronegativity goes down, and therefore it easily gives away electrons because it can barely hold on to them. Do you guys get what I'm saying? Awesome. So that's the trend in the family, and you know what's coming up next, right? Group, all right, or period, group, period, I don't know, whatever you want to call it. Right. So remember, in the period, every time you take a step to the right, every time you take a step to the right, you're adding another proton, right? So remember, in a period, you have the same number of shells, the same number of shielding. However, every time you take a step to the right, you're going to add more proton pull, and those little things are going to get pulled in tighter and pulled in tighter and pulled in tighter. So man, if they're getting pulled in tighter over on the right, guess what's happening to electronegativity? Like way up, absolutely. So the electronegativity increases from left to right across the table. So it kind of looks like this, right? You're going to start out, well, you know what? Let's give me a little bit of leeway here because I'm going to have to actually draw here. So it's going to start out like this, like big, and then it's going to get a little bit smaller, then it's going to get a little bit smaller, and it's going to get a little bit smaller, and it's going to get a little bit smaller, just like that. And so now, if you have the radius in your head, you know what's going to happen to the electronegativity, right? So the electronegativity out here, right, the distance, and again, it's all relative, the distance between this nucleus and these electrons compared to this nucleus and these electrons, you can see where one is much closer than the other, right? And just like magnets, the closer they are, the greater the attractive force. So this is going to have a very high electronegativity. That's the incorrect kind of high, but I don't care. That's funny. So again, as we move to the right, the electronegativity is going to increase because it's inverse or like opposite of the radius. Dig, dug, awesome. That means that the atoms, the elements over to the right, these guys are going to take electrons, which kind of make it's just the pattern of the periodic table. Because remember, metals are over on the left. This is where you have metals, and metals always lose their electrons because they're huge. Whereas over here, those are nonmetals. And nonmetals are always taking electrons because the radius is so small and they have such a strong electronegativity, man. They just bump into something, take away their electrons. They don't even care. They're just taking them like little electron thieves. All right. So, oh, hey, I wonder if I can, yeah, let's just keep going. So another vocab word that we have here is reactivity. And this basically tells us how easily an atom reacts when it comes in contact with other atoms. And I don't know if you can guess, but as far as reactivity goes, it's going to be something like this guy and something like this guy. Like the extremes. Like the ones that are extremely large atomic radius are going to be very, very reactive because they cannot hold on to their electrons. So they just sort of fall right off, bam, chemical reaction. Same thing, only completely opposite, is over on this end. The very, 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 very small atomic radius is going to be very reactive because they have such a huge electronegativity. They just rip electrons off of any old atom that comes in. They don't even care. Just take them, right? Like really, like it's the extremes that are highly, highly reactive. Same thing with wait, where did it go? Oh, up right here it is. Right here. Like this guy. The atoms on the elements on top are going to be more reactive because they're smaller, and then the elements on the bottom are going to be like more reactive because they're really big. Do you guys get what I'm saying? I hope so. Anyway, let's move on. So the reactivity thing, what I just said there, right, with the whole atomic radius thing. If you remember, there's the squiggle line that goes like this, right, on the periodic table. Right? And the most metallic things, you go way down and left to be the most metallic. Right? And so we said francium is the most metallic because it's all the way down and left. Same thing, only completely opposite. You go up and right to be for nonmetals. Oops. And for that, it's fluorine. The most non-metally of all the non-metals is fluorine, right? So, like I said, or maybe I didn't, I don't know, but let's say it again. Metals lose their electrons because their atomic radius is so stinking big and they have such a weak electronegativity. Well, if electronegativity gets weaker to the left and to the bottom, that means that francium has the weakest electronegativity that you can have, and therefore reacts just so readily. I mean, this francium is like ready to go. It reacts at the drop of a hat. With anything, francium will react because it simply cannot hold on to its electrons because it's way huge. It's like so big the electrons fall off of it. Now, the same thing, only opposite. I mean, the same idea, the same concept, is that fluorine is so highly reactive because that radius is so small, it's so compact. The electronegativity is through the roof. It is the highest electronegativity of any element in the universe is fluorine, right? And that's why fluorine is so reactive. So it's these extremities, right? It's like the one in the bottom left and the one in the top right, ignoring the noble gases because they don't do anything. That's where you get your most reactivity because they're like the most extreme with atomic radius. I mean, does that make sense, you guys? I certainly hope so. I'm just going to pretend like it does because I can't really tell because you're in there. And I'm not even here right now. This is like recorded yesterday or something. How do we have a conversation like that? Anyway, here's what I need you to know. I need you to know that for metals, the activity increases at the bottom of the family and to the left. So for metals, it's like this. Okay? So for metals, it's bottom and right. And for non-metals, the reactivity, or they call it activity, like how well it reacts, is greatest at the top of a family and increases to the right. So for non-metals, it's like that. Got it? And again, these are trends. It's not like an absolute 100%. Everybody wants science to be like absolute cut and dry. Like if you go top and to the right, it's every time more. Like, no, this is generally speaking, right? Okay. I just want to make that very clear because nature is never, ever as simple as people want it to be. People want to have all the answers and they want it to be really nice and clean with nice straight lines. And nature doesn't have straight lines. It's all fuzzy with little squiggles and every exception under the sun because otherwise we would have figured it out long ago. But here we are, still trying to figure it out. All right, now the next thing that we're going to talk about. So we have radius, we have electronegativity, and now this next thing is ionization energy. So ionization energy is very much related to electronegativity, but it's sort of like different. So electronegativity measures how strong an atom pulls electrons in as compared to other atoms. Like when it bumps into another atom, how strong can it do like a tug of war for the electrons? Now ionization energy, on the other hand, this stuff is just a wee bit different. Ionization energy is the amount of energy needed to remove a valence electron. Okay, so it's like how much energy do we need to shoot at this thing to break off, and it's literally this. This guy right here, this is ionization energy. He represents the amount of force or energy it takes to break off that first valence electron. Well, the first ionization energy is breaking off the first, and the second ionization energy is breaking off the second. But it kind of measures, it's a different way to measure the same thing, right? So if ionization energy is like really, really high, like if this dude is like muscles like this, it's huge, right? That means that probably going to be like not losing electrons, probably going to be pulling electrons into itself. It's just sort of another like way for us to know. So ionization energy and electronegativity, they kind of go hand in hand, right? They are very much related. If ionization energy goes up, so does electronegativity, because they both measure how that electron is pulling electrons in toward itself. Does that make sense? Whereas atomic radius, that just measures how big something is, right? Like how big the atom is. And it kind of makes sense that the bigger the atom, that like the further away those electrons are from the nucleus, like so as atomic radius goes up, those two energies are going to be going down because they're far apart, and far apart makes it hard for things to stick. Okay? Well, I hope so. So what do we got next? Oh yeah, what affects ionization energy and electronegativity? Well, it's pretty much the same thing, man, as before. If you're in a period, again, this is really, really important to keep the idea that like these trends only work in a period or a group, okay? So yeah, so same thing with electronegativity. Every time you take a step to the right, you're adding more proton pull, and there's the exact same amount of shielding. So as the atomic radius gets smaller, the ionization energy goes up because those electrons are closer to the proton. It requires a lot more energy to rip those puppies off. Do you guys get what I'm saying? I'm sure you do. So the greater the distance from the nucleus, decreases ionization energy. The shielding effect, more shielding gives you lower ionization energy, which means if you have a bunch of periods like this on the periodic table, that means that down here you'll have lower, and up here you'll have relatively higher. Which is kind of like the exact opposite of the radius and stuff, because it's the exact opposite. Radius gets bigger, ionization and electronegativity gets smaller. So like I said, the greater the nuclear charge in the same period, the greater the ionization energy, because there's more protons there to hold onto the electrons and make more proton pull. The greater the distance from the nucleus, or like from the protons, decreases ionization energy. So anytime you can get that radius bigger, you're going to decrease the ionization energy. And also more shielding lowers ionization energy, because more shielding means more radius. It's like this whole thing. Like once you get it, they all kind of like affect each other. Now the same thing, different. We're going to do group now, right? So trends in the group. As you go from top to bottom, or increasing atomic number, the ionization energy decreases. Now, why would the ionization energy decrease if you start out with something that's like that, and then the next thing is like that, and then the next thing is like that, and then the next thing is like that? Why would that be? Let's think. Well, down here, could it possibly be, like, let's think, down here, the electrons are going to be this far away, and with this one up here, the electrons are going to be that far away. So who's going to have the more proton pull? Well, you little stinker. Right? Right, yeah. So that means as you go top to bottom, in other words, every time you take a step down, the first ionization energy decreases. Why? Well, one, the electrons are further away from the proton, right? So you take a step down here, you're getting further away than you were at the one above. You come down here, you're further away than you were at the one above. So it gets, the further and further away you get, the ionization energy almost drops to like near nothing. Also, more shielding, right? Because as you remember, every time you take a step down, there's an inner layer in there blocking it. So this one has two inner layers in there. This guy has 1, 2, 3 inner layers. So there's just, every time you take a step down, bigger radius, lower ionization energy, because further away, because more shielding. Got it? Good. All right, so generally, it's going to increase from left to right because there's more protons to attract. Same shielding throughout the period. Let's call it a day. What we are going to be working on for this one is trends in the periodic table. I think that's like a multiple choicey thing. I think, give me like 2 seconds here. Let me just check something out. All right. So I found for you this thing. This is the worksheet that we're going to be working on that's associated with these notes. So here's the thing. Everybody tends to get really confused with this. So I want to iron it out now. This area right here, right, this is all just like a quick summary of the notes that we just went over. And this is just a picture of the table. That's all, right? Like oh, metals, nonmetals. What is this? Oh, yeah, look at that. That's just nonmetals. I guess that's the atomic number, and that right there is the, oh, yeah, atomic number, electron configuration. Yep, atomic number, electron configuration. That's all there is to it. You don't have to fill anything in. Everybody goes in here and just tries to fill this in with something. Don't do that. Just come here and answer these questions, right? These are like just a bunch of multiple choice questions based on the reading. And also, I want to point something out. Where can I find? Oh, yeah, right here. Let's look at number 18 for a second. So number 18, if you see, it's got this like blah, blah, blah at the bottom of group 17. Right, and then there's this Roman numeral and then A. This is like a really old version of numbering the periods. I'm sorry, of numbering the groups in the columns in the periodic table. It's like old school. Dude, I was in college in the early 90s and we didn't use it back then. We just did 1 through 18, but they keep it there. I'm not really sure why. So I just want you guys to ignore that and just go with the actual numbers like groups 1 through 18, because that's what we're doing. Okay. So that's it for today. I hope you guys had fun. Lord knows I did too. And I'll see you on the flip side.